Abhishek, you're picking up.
Hello, everyone, and welcome to Berlin Machine Learning Meetup, another online version. And today we have, as usual, we have two very interesting speakers and two very interesting talks. If you have any questions, feel free to ask in the YouTube live chat. And now I will hand over to Trent to introduce our first speaker for tonight. Trent.
Hi, everyone. Hello, can you hear me?
Yes.
Great, awesome. So hi, everyone. Great to have you here in August edition of our meetup. And like Abhishek mentioned, two speakers. So I will introduce the first now, and then when the second comes, I will introduce the second. So the first speaker is Jim Dowling, and he's CEO of Logical Clocks and also an associate professor at KTH Royal Institute of Technology. He's lead architect of the open source Hopsworks platform, which is a horizontally scalable data platform for ML that includes the industry's first feature store. And today he's going to be talking about GANs for anti-money laundering. And I'll skip the abstract because I'm sure that Jim will get right deep into this. So thanks for joining us, Jim, and please take it from here.
Thanks, Trent. Okay, I'm just going to share my screen and hopefully we'll be ready to go. Are we good, Abhishek? I'll just hide this thing down here. Go back to the beginning. Yeah. Okay, thanks everyone for joining. So I'm going to talk about anti-money laundering and how we used GANs to help identify financial transactions as either suspected for money laundering or not. These slides are available right now. If you Google SlideShare and my name, Jim Dowling, you'll find them as a link there if you want to jump ahead or follow along. So what I'm going to talk about is the basic problem of anti-money laundering and how we want to increase the detection rate, so identify more transactions as money laundering and also reduce the costs for money laundering. And the solution we used was deep learning, and not just any deep learning, but generative adversarial networks. And we worked with a very large data set. So we worked with 40 terabytes of training data. And we used technologies such as Spark for feature engineering. And we also use TensorFlow and GPUs to train a classifier, binary classifier, that would identify transactions as either clean, they're good transactions, or dirty, and they're suspected of money laundering. And we use the open source Hopsworks platform to do this work, and I'll talk a little bit about that while we're during the talk. Now, there is a reference white paper, you can read up more details on this, but I'm just going to jump in. So what is money laundering? You've probably heard of it. It basically involves taking dirty money, which can come from places with dubious corporate financial structures, or it could be drug money or any type of money that's been illegally acquired. And you want to turn that dirty money into clean money. That's probably more difficult to do with the crackdown on jurisdictions that have traditionally been sources of money laundering in recent times. And now a lot of money is flowing into, for example, European banks from less credible areas, and it's an increasing problem of identifying whether the money coming in is dirty or clean. So if you're trying to do money laundering, which I wouldn't recommend you do, but if you were, you have to identify these different steps. First, you have to place the money, and in technical jargon, that's smurf it. So give that money out to people who have valid accounts, for example, at financial institutions. You want to spread that money out from those locations, and you want to do it fast before the systems can identify you. And then you want to pull that money back together to locations where you can actually use the money to buy real concrete assets. And I don't mean football clubs, but any type of asset that can now is more difficult to take away from the person who's bought the asset. So you can see a graph on the right-hand side. I'm going to use a pen just to highlight some things. So we can see that we have these nodes here. We can imagine our customers in a financial graph, and the edge is the transfer of money between them. So we can see that this node that I've highlighted has engaged in this large number of transactions. And if we assume that the size of the node corresponds to somehow the amount of money that was involved over the edge, then we can see that this one has lots of transactions, either in or out. It's an undirected graph here, but it's just a visualization to give you an idea of the type of tactics people have. Lots of small transfers of small amounts of money go to hub nodes who aggregate the money and then further to integrate that money before it can be taken out and used in the real world. So what do we have today? Why is deep learning interesting in this domain? Well, currently, the state of the art is rules-based anti-money laundering systems, just like we had for example, virus checking software years ago. We had a big database of rules, and we tried to see if rules are matched, so patterns of behavior are matched. If the number of transactions in the last hour is greater than 10, and the amount of money being transferred is greater than 50,000, and we suspect that this is not a good bank, we should send some alert. And some human will then investigate whether that particular transaction is money laundering or not and adjudicate whether it is. In the deep learning world, what we're going to do instead is we're going to train a model. And after we've trained the model, we can use that model to predict whether a given transaction is suspected of money laundering or not, and then alert based on this. Now, in practice, we're going to keep this system until the regulator says it's now deprecated. In the moment, what we can do is we can integrate both systems, and we have better coverage, hopefully, of the money laundering technology out there, with better prediction capability for identifying transactions as money laundering. But hopefully, in time when regulators agree with it, these machine learning approaches will be approved and can be used to help identify money laundering. So if we look at money laundering as a supervised machine learning problem, we can see that I said we had 40 terabytes of transaction data, but we have a big problem. We have a class imbalance. We can have billions of clean transactions and only a few thousand dirty transactions. So the traditional machine learning, supervised machine learning approaches to upsample the smaller class or to downsample the majority class, they won't work in this case. That's one of the problems we have. The other one is that well, there are plenty of other ones, but let's get to the next ones on the next slide. So another problem that we want to really address here is that even if we try and measure the F1 score, because it's a binary classifier, we can say, well, we had a lot of true positives, and that meant that we predicted a dirty transaction. It was a money laundering transaction. It was dirty. This is very good. And if we predicted that it wasn't a money laundering transaction, it was clean. This is good. But the other areas which are more interesting are false negatives and false positives. If we predict that a transaction is dirty, but it's not, we have to do a lot of work. And currently, banks employ hundreds of people who investigate these alerts to find out whether the transaction was money laundering or not. It's a cost. But what's worse is that if you predict that a transaction is clean, but it's not, it's a money laundering transaction, you can get huge fines. Fines can be billions of dollars potentially. So what you'd like to do is have some variant of the F1 score that doesn't evaluate all of these potential cases, the precision, the recall, fallout equally. We want to avoid false negatives. So what we did was we approached this problem as an anomaly detection problem. And anomaly detection follows on quite naturally from supervised models. The traditional approaches to unsupervised approaches to anomaly detection, like k-means clustering and PCA, don't scale. So it don't scale to the large volumes of data that we have. So we approached it as a semi-supervised anomaly detection problem. We have a small amount of data that has one class of label, and we have a large amount of data with another class of label. And basically, we see this. This is a T-shirt we printed, actually, and we got everyone in our company has it. We see the future. The revolution here is not fully supervised; it's semi-supervised. And GANs are a very interesting technology for doing anomaly detection. There are other technologies in deep learning, so variational autoencoders are used, but they're not state-of-the-art in terms of performance. So there are a lot of different approaches to doing anomaly detection with GANs that are out there. I'm not going to go through all of them individually in detail. One of the problems that you really want to address at the beginning is if your data is not anomaly-free. So we're going to train with an anomaly-free data set. And in the case of money laundering, we know in the Scandinavian banks, there was a lot of money laundering occurred in recent years. And the transaction data that you may have there might include some transactions labeled as not money laundering, but in fact they were. So ideally, you want to make your data set as anomaly free as possible. There are some techniques you can do to get around it, but in general, this is your goal, to make it as anomaly free as possible. There's a link to give you some techniques from a paper if your data has anomalies and what you can do about it. In general, and there's a very good workshop from NIPS in 2018 about anomaly detection and GANs, and they talked about the architecture and the convolutional architecture itself, which is often used in a lot of GANs. So you may have heard of DC GAN, which is a well-known convolutional architecture for GANs. This is often more important than how you train them, is a claim by Mark Granazzo. But what we'll look at is the first approach that we looked at, and we looked at what we call a GAN discriminator-based anomaly detection approach. We basically started out with all of our transaction data of what we call the clean or good transactions, and we trained this discriminator to basically identify these as, and they were labeled as good transactions. Now, the GAN approach is to take random inputs, and over time, what's going to happen, the random inputs will generate sample transactions, so money laundering transactions, financial transactions that we're going to label as being good or bad. At the beginning, the discriminator will label them as bad because they are bad. Random data is being created as transactions. We're going to have random data in here. But what we're trying to do is train this generator to model the data distribution of this input good data over here. So over time, that we'll have a loss function here, which will be used to update the weights in the generator. So that generates transactions that are similar-ish, good enough to fool this discriminator to think that the transaction that arrived from our generator is in fact a good transaction or a correct transaction. Now, once you've trained this model, you can actually just strip off the discriminator and pass new transactions into it, and it will label them as good as bad. And this approach we did just to get started to see if it would work, and it was kind of interesting, but you encounter quite a lot of challenges, right? So you have the problem of picking the right GAN architecture. Mode collapse is something I'll talk about in a second, and then it's very hard to find good hyperparameters because they're really sensitive to hyperparameters, GANs are. So for the mode collapse problem, the problem we have is that our transaction data is multimodal. Right? You're going to have different types of transactions. You're going to have payments for goods and services. You're going to have money being transferred between parents and their children. And these different types of transaction behavior will all be perfectly normal. But in traditional GANs, they're kind of based on reaching Nash equilibrium. And they often will not learn these different modes. They'll learn to produce only a small number of nodes. They'll reach Nash equilibrium, and what we call mode collapse occurs. They won't be able to learn different types of transactions that are in fact perfectly normal. The other problem or challenge we have with GANs is that they're very highly sensitive to hyperparameters. And there's a really nice website here you can go to find out a list of tricks for how to tune those hyperparameters and what kind of other hacks help GANs to converge. But it's essential to have good optimization and hyperparameter tuning to be able to train GANs. So how do you address the mode collapse problem? Well, there's a bunch of different approaches that have been described in the literature. You can have multiple generators where each generator is for a different mode of distribution. This is if you have some sort of prior on your data and you know the different modes. It's quite a hard, it's not a generalizable solution that you can use. F-ANO-GAN is an interesting approach based on deep convolutional GANs with Wasserstein GAN. And this introduced an encoder, and we'll talk about this in a little bit in a couple of slides' time. And the encoder was trained after you trained your GAN to basically help identify the points in our space that generate interesting transactions, the transactions that can fool our discriminator. And we're actually built some of our work on top of an extension to F-ANO-GAN developed by our compatriots at Linköping University in Sweden. And that parallelizes the training of the encoder and generator. And I'll get to that in a second. Okay. So this is the approach that I was mentioning. So it's basically the same as before. We have a generator, we have a discriminator. We're going to have our random input vectors played in here. But now what we're going to do is, after we apply the generator to generate our sample transactions, we're going to feed them through the encoder to try and recreate this point in latent space that was used to generate the original transaction. So it's similar enough to before, but now we're training the encoder, and we're going to train it in parallel with the generator. And we're using the distance function. We're using now the loss function from our discriminator back to the generator is going to be a Wasserstein GAN. A Wasserstein GAN is not, it's not going to tell us, yes, you're correct, no, you're not correct. It's going to give us a loss, and it's going to say an approximation of how far away our fake transaction is from a free, from a correct transaction drawn from the original data distribution of good transactions. And that's using a gradient penalty as part of it. So what you get when you're finished training your Wasserstein GAN GP model is that we don't keep the discriminator anymore. We keep the generator and the encoder. And in fact, what we do is we feed our transaction into the encoder. The encoder will take this transaction and turn it into the input vector, which was used to generate a sample transaction. So we're going to generate this input vector from the encoder, and then this input vector we're going to feed through the generator, and it's going to give us back the sample transaction. So we're trying to, like a normal variational autoencoder, we're going to try and recreate the input signal. And the detection of anomalies is basically a function that computes the difference between the input transaction and then the recreated transaction after we've gone through the encoder and the generator. And you can read this paper for more details on the approach, but basically we found this is a better way of doing anomaly detection with GANs that has less risk for mode collapse. But we still have the issue of hyperparameter tuning, which I'll get to in a little bit. So before I get to that, does GANs work? Does this help improve money laundering, anti-money laundering? There's a paper from a bank in China who claimed that they reduced losses of 10 million renminbi in 12 weeks by using GANs for telecom fraud detection at the receiving bank. We've seen in our work that it has a massive improvement over the state of the art. And you can read this talk at the Spark AI Summit in 2019 by Swedbank to find more details. So here's a couple of getting this platform into production, right? Because this is just the general big picture of the algorithmic challenges we faced. But how do we get all our features that we're going to use for this GAN into the AML application? You'll have some low latency features that come, for example, in real time. So the customer, when the customer executes the transaction, we call this real-time features. We have the IDs of the customers transferring money between each other, the amount of money they're transferring, the type of transaction, the time it happens, and you can have the bank IDs as well. But there's going to be a lot more features than that. We have counts of the number of transactions that the users have performed in the last hour, the last day, the last week. Maybe we'll have updates from operational databases. Maybe we'll have data related to the credit worthiness of these customers. We have something called Know Your Customer data that banks typically all manage. So all of these features we use to train the model. And another one that we spent a lot of time working on are called graph embeddings. So being able to compute an embedding of the recent transactions that a user has engaged in. You basically take a random walk of recent transactions within a given time period, and you convert it into a high-dimensional vector that represents that subgraph that you're interested in. And that helps you get around some of the problems of users doing small micropayments that get under the rule-based threshold. But when the pattern of payments that they create is captured in our graph, it becomes easier for us to use that feature to identify money laundering. So what a practical system could look like is the following, and this is based on our Hopsworks platform, what we can do. Your anti-money laundering application there will have these 7 features that come in real time, but then it has to look up another 200 plus features from the online feature store, okay? And those 200 features it wants to get back in very low latency, so 10 milliseconds to 50 milliseconds. It builds the feature vector, and then it makes the prediction. And we call that the online feature store. For the 40 terabytes of data that we use to train the model, we store that in the offline feature store. So it's really only the features that we need for the real-time predictions that we store in the online feature store, it's a smaller subset of data, and the larger set of all historical data we store in the offline feature store. And we provide a data frame API so that it makes it easier for you as a programmer to do your feature engineering. You can compute the transaction counts in a streaming app in PySpark or in Spark or even in Flink, and then register them with the feature store, and they'll get registered with both the online and offline. And so we ensure the consistency of features between both these online and offline stores. And when a data scientist wants to create a training data set, for example, they might want to create it in TF record format because they want to work with TensorFlow, or maybe PyTorch, so they want NumPy files. They can basically join all the features together that they're interested in, and then they can materialize that training data to a file system. So in our case, we have our HDFS-based file system, Hopsfs, but you can store it if you're running our platform in S3 on AWS or ADLS on Azure, or GCS on Google Cloud. Basically, this makes it very easy for data scientists to create new training test data sets with new features in the file format that they want to use for the framework they want to use. In this case, for deep learning, it's typically going to be PyTorch or TensorFlow. Now, how this fits into the end-to-end model of our whole platform, and how we put something like this into production, we start out with our raw data, and we have our engineered features in the feature store. And this helps the data team faster backfill features, train data sets easy. But then for GANs, we have the problem of how do we do hyperparameter optimization? If you're really doing this properly, you'll do ablation studies to understand the relative impact of the different parts of your model, so the different layers, the different regularization components, the different hyperparameters that you set, the different features even that you use. So these things we can all run in parallel in our platform. And we can also train models in parallel in our platform, and we can also serve models on the platform. And that's using Kubernetes to serve models on Docker containers. But I'm going to talk a little bit about how we track all of this end to end. So if you're interested, we had a talk last week at Usenix's OpML conference about what we call provenance or implicit provenance. So when we're training these models, we're going to read our data sets and our training data, and we're going to save models, and we're going to do hyperparameter optimization. And this is all pure TensorFlow code. And you may have heard of frameworks like MLflow or TFX, TensorFlow Extended. And what they'll ask you to do at this point is really to add lots of lines of code. So pollute your code with calls to say log this, log that, log this, log that. But what we try to do differently is that you can write pure TensorFlow code or Keras code, and we're going to use conventions in our platform. So we have well-known paths, such as the feature store path, the training datasets path, the model path, the logs path, notebooks path. And when we see that data, for example, training data sets are created, feature groups are created, models are saved, these events happen at our file system, and we can then index that data so that we can later search for it. And this means you don't need to change your code. So many events in our machine learning pipelines can be indexed and identified this way. So I promised you that we look at hyperparameter tuning a little bit. This is a little bit of the code, just a kind of a template of the kind of code that you have. You can see that you have a lot of hyperparameters here. So rather than just fix all of them based on some paper that gave us some recommended values, you might want to explore them. And exploring them basically means going through some phases. You explore your hyperparameter space, your model architecture, you do experiments, you do training on lots of GPUs in our case. So our platform provides experiment management support, kind of like MLflow. You can run experiments, and then you can go back and look at them. And I'm going to show you how we integrate this. And there was a talk at the Spark Summit last month about this. It's called Maggie. But the problem that we're trying to solve with this Maggie framework is that when you go through the many different phases and you're designing your model architecture, and then you want to do some hyperparameter tuning, maybe you'll do an ablation study, and then you want to train on lots of GPUs, you're always rewriting your code. So you might end up with many different folders, one for each of these different phases. So what we've done is we've basically tried to address this problem by saying, well, we shouldn't have to rewrite our code between the different phases. So we introduced an abstraction called the oblivious training function. And in this, you write the training function once, and you can reuse it when you're just running on a Python kernel on your Jupyter Notebook on your laptop, or whether you're doing hyperparameter tuning on a large cluster, or parallel elevation studies, or distributed training. So the basic idea is that your code on your laptop will stay the same as when you're running it on a big cluster, and we use Spark to distribute the training and the hyperparameter optimization. The API for Maggie looks something like this. We start down here, we define a search space, and then we say run this experiment, and the function that we're running is this one here, the AML function. And this is our hyperparameter search space. The type of optimizer we can use is random search. We actually have support for quite a lot of new ones, not just random search, grid search, and Bayesian optimization, but even ones that tune the amount of resources that you contribute to each trials. So basically, this function, this training function, will get run at many different containers, on many different containers with one GPU each, and then we'll aggregate all the results of all these parallel hyperparameter trials and help you figure out what good hyperparameters are. This Maggie framework is run on top of PySpark. It's open source, so you're free to go ahead and try it out. But what I did, I'm going to go through some code for the last 7-8 minutes that I have left. If you're interested in the AML problem, there's a data set on Kaggle. It's called the PaySim AML dataset, and the link is provided below. And they talk through many of the different features, some of which I've talked about already. Graph-based candidate features, the frequency ones, where we look at the number of events that happen in the time window, amount of magnitude of money transferred, for example, and then sudden changes in features and things like that. So I'm going to use a platform called Hopsworks AI. It's a managed platform, a managed version of our Hopsworks platform. It's free to use right now, so it's in free beta. It's running on AWS. It'll be in Azure within a month, and you can register an account there, and we won't charge you until October, I promise. And just to tell you a little bit about what it does is it'll deploy a Hopsworks cluster. You can integrate it with things like Active Directory. It can run with an IAM profile to integrate it to get your data for feature engineering from S3 or Delta Lake or Redshift or wherever your data is. And you can also use it from the feature store. In particular, you can use from Databricks or SageMaker or Kubeflow if you're using those platforms already. But the platform can run these Spark jobs and these deep learning jobs for us. So I'm going to look at how we do it. So it's open source. The SaaS platform is available at Hopsworks AI, but you can install the community version, which is fully featured. Some of the integrations with Databricks and SageMaker and Active Directory are not in that. That's what's in the enterprise version, and Kubernetes as well. So I'm going to go through this demo that I did briefly with this Kaggle dataset. So this is Hopsworks AI. You'll need to, if you want to use this and register an account, you can get a free demo instance. But if you want to spin up a cluster, what you'll need to do is set up something called a cross-account role. And this is the same as Databricks. You'll need to add that to your AWS account so that we can launch a cluster in your AWS account. So I'm just going to spin up this cluster here. I'm already logged in. I already created a project here called AML. I can zoom in a little bit so we can see it a bit clearer. These things are called projects. They're like GitHub repos. You have code, but you also have data and members of them, and they're completely isolated from one another. But you can run this feature store tour if you want to get started with the feature store. I'm going to look at the AML one. I'm going to spin up a notebook. Let's just do, we can do a Spark one to begin with. So I'm going to spin up a notebook. These notebooks can be run as jobs, actually, if you're familiar with how Netflix work. We enable notebooks to be run as jobs. So you can put these in pipelines, and you can run them with Airflow pipelines, and Airflow is also included in the platform if you want to use it. So I'm going to talk through this notebook briefly here. We have a data set, and I uploaded the data set to my platform already. It's called paysim.csv. I need to do some feature engineering on it, right? So one of the points of our feature store is it requires lowercase names for the features. It's an artifact of the fact that we use the online feature store as MySQL cluster, the offline feature store is Hive, but it's a little bit awkward, and we can see that inferring the column types didn't work, so I have to cast one of them to integer type. I added a couple more features, but basically this is a very simple Python application in Spark, PySpark. And it's read up this data frame. We've done our little bit of feature engineering, and now we create a feature group in the feature store with these features. These are the anti-money laundering features, And then we'll be able to use them to create training data sets to train models for identifying transactions as fraud or not fraud. Other things that we can do with our feature groups, these are the groups of features that we've computed together, is we can attach tags. You can put arbitrary tags in here. This tag is called privacy level, and I said it's PII, or personally identifiable information. And that tag will get attached to the feature group, and we can actually search then globally for any tags for features or for names of feature groups, and they can be in any of the different. You can have, so I search for something called players, and I find this feature store here, which is actually in, sorry, that feature group here, which is in a different feature store. So typically organizations want development feature stores and training and production and staging. So let's go back, and I assume this is going to be finished. It's not quite finished yet. Run the AML example here. So I started running this code to generate the feature group, but I can show you one that I built already. I can go into one here. So here we have one here. And this one has, we can see if we look at the details, we can see that there's 27 features and 7 feature groups, 2 training data sets. And each feature group that we look at, we can get we can do some exploratory data analysis, look at correlations between features, distributions of given feature values, cluster analysis, and so on. You can create training data sets by joining together features from different feature groups, and you can create them in the file formats that you want to use. And we maintain statistics for them. And if we go back, let's see, have a look here. We've got this one. So we just created one feature group here, in fact, the PaySim one. And if we go and look at the equivalent statistics here, we only had this many feature groups, and we can look at, there wasn't a very wide distribution in the amount of and same with the balances. So this data set is not, yeah, the world's best. We can have a quick preview of it, which is kind of nice to get started. We can see here's some data. We have some step numbers, the action, the amount of money transferred, the original account, the destination, and so on. And we can just go through and we see whether it's fraud or not. So the feature store helped us out a lot there. I'm running low of time, so I'll just show you basically how we do it with Maggie, how we do the hyperparameter tuning. We define a search space. Well, then we define our training function. In this case, we will have our GAN in here, and then we can run an experiment. So what this will do is it will run in parallel training over as many GPUs as you have. And when it's finished training, we can look through experiments and get some of the experiment results. We can compare different hyperparameters here. We get a metric that we output. I wasn't outputting a very interesting metric there. But you also get tensor boards. I can show briefly a tensor board from a different projects. I didn't create one there. And so we in our ecosystem, we're supporting as many Google tools, not just TensorBoard, but also What If tool. And I think I need to refresh that. It's going to take a second. This is a very nice way of, in this case, if we want to manage. So in this case, I need to select all of these runs, toggle all runs. Okay, that's how you do it. So we toggle, so we can see all of the different runs here that I did earlier. And if we show wall clock time, I think I only had 12 executors. So it did 12 experiments in parallel. And as those experiments finished, a bunch of new experiments were started, and eventually it all finished. Now, in TensorBoard, you have this very nice hyperparameter view that you can use, which is a really nice way of examining hyperparameter experiments. Okay, I'm running out of time. So what I'm going to do is I'm going to jump back and finish up. So let's present again. So yeah, just to summarize, so what we did was I looked at anti-money laundering as a problem. We modeled it as an anomaly detection problem with GANs. And some of the challenges we had from an engineering perspective were how to manage those features to make them available so that you can have an online AML application that can pull the features in real time from a feature store. But also we had challenges in training the models, and we had to use as many GPUs as we could get, not just to find good hyperparameters, which I talked about, but actually we did distributed training as well, which is supported in the platform using distributed TensorFlow. We're a European platform where I think we have more Germans than Swedes in the team right now, which is not surprising. We're open source, so you can follow us on Twitter, you can star us on GitHub, and you can try out the platform at Hopsworks AI. So I think that's it, and then I'll take any questions if there are any. I'll stop sharing my screen, I guess.
Thank you very much for your wonderful talk. There are a lot of questions, but actually, I guess one of your coworkers was answering most of them. So
okay, so David,
but there are a couple of questions still open. The first one is in the very beginning you talk about that you wait for an approval of the machine learning approach. How are they evaluating that? I mean, do they do like testing as we do in machine learning, or how is that?
Yeah, it's a really good question. Yeah, I'll stop sharing the screen there. There we go. Okay. Yeah. So I think the issue right now in Europe is that I don't think we have European-wide regulation. So you have different regulators in different countries and in different countries who will have different approaches. And I know we've had contact with people in the UK who have a regulator who has a positive attitude towards this. I think most of them do. If we present enough evidence that these approaches, not just that they work and work better, but that they have some level of accountability. I'm not going to say that they're fully explainable, but accountability, then I think that, and what we're trying to do, at least from an engineering perspective with Hopsworks, is we have put in a lot of engineering effort on provenance. So being able to take a model and say, these were the features that were created, this is the training data set used for this model. These were the features they were created that used to create this model at this moment in time. So those features that we take from the feature groups, when we use a framework called Hoodie, we can say, okay, what did the feature group look like at this point in time? We can say, okay, the training data set was created on the 1st of January, 2020. Now I can create exactly the same training data set, even if that training data set gets deleted later on, because the underlying feature groups have this ability to go back in time to get a snapshot of the data of the features at that point in time. So I think, this transparency and ability to explain anomalies in your data, because often we find that bias in models creeps in through bias in features and feature groups, and being able to detect them earlier with the feature store will help. But ultimately, we have a problem with, and I think also I mentioned ablation studies, they will help a lot. So being able to do things like leave out features to say, for example, we have this graph embedding, which is a very good way of predicting these dandelion style patterns of money laundering. If we remove that and we can see that those transactions were that particular feature, if we remove it, it's a vector, a graph embedding. If we remove it, retrain the model and reevaluate the model, and we can see then that those transactions were identified with the help of that feature, then that adds some level of explainability to our deep learning black boxes.
Mm-hmm. Is any of the money laundering data open source, available to others?
I linked the PaySim data. It's a Kaggle competition. I think that's the best one out there.
Okay.
And it's actually based on a platform called Swish in Sweden, which is now a verb in Swedish. It means to give me my money. Swish me some cash.
Cool. Then an organizational question. You referred to, you said so in the very beginning of your talk, but where can the slides be found? Other people were asking for it.
I'll pull up the link. I mean, it's SlideShare. So if I go to my own SlideShare, I guess I'll get it. If you Google Jim Dowling SlideShare, you'll get it. I don't think there's that many Jim Dowlings in the world that write on SlideShare. I can paste it into the chat here. I don't know if that helps everyone.
Okay, yeah. And then while you're at it, the link to the white paper is apparently not working. People checked it out but couldn't access it.
God. Someone will be fired.
Yeah.
That's me. Sorry. All right. Yeah. No, it's Sweden. We can't fire anyone.
Then there was, I guess, a simple question regarding the F1 score you referred to. In what way did you adjust it to account for the highly unbalanced data set you're talking about? Is that the usual way?
You don't want to miss dirty transactions. So like your system is not better than the existing rule-based system if it misses any fraudulent transactions or dirty transactions that the existing system catches. I mean, that's a hard. Now there's an additional challenge is what happens if you find loads of transactions in your historical data that you've marked as fraudulent that were marked as good, and you're like, oh. That's a different political challenge.
Yeah. Then one other question was, how do you validate the results from the generator and the discriminator? How do you do that?
Well, I mean, so we used our as holdout data. We had this the bad transactions or dirty transactions. Okay. And we use that as holdout data, and you can do some synthesis to an upsample to create more, test validation data with that. You can also generate. I mean, in this case, what you're trying to do is evaluate whether your data is out of sample or not. So the easiest way to do this is if you're doing time series data, take your data from the year 2010 to 2019 as your training data, and then keep 2020 or 20, the last year as your test data. So there's the combination of both of those things that you can do. So actually the feature store helps a lot there, because you can just go, hey, give me training data from 2010 to 2018. And then you say, give me another another data set from 2019 to, or 2018, 2019 or something like that.
While you're at it, feature store is a product on its own, right? And the question is
oh yeah.
Sorry,
it's the standalone. I mean, the platform is modular, so we have customers using just the feature store, like Databricks and SageMaker customers.
I see, but it's also integrated in the Hopsworks service.
Yeah, it's something that we did early, and I think we're the first open source. We're still the only fully open source feature store out there, as far as I am aware.
Cool. Jim, thank you very much for your talk.
Great.
And I'll give the mic to Trent.
All right. Yeah, Jim, thank you very much too from my side. Really excellent talk, and I learned a lot, and I really appreciate the practical examples and whatnot too. So now we will move on to our second speaker, and it's our pleasure to have Maurits Kaptein speak. He spoke. Maurits, was it about a year and a half ago you spoke with us before?
I guess it was winter, so it must at least be half a year ago. So I guess it's 1.5 years ago by now.
Yeah, yeah, cool. So so Maurits is back, and this time he isn't traveling to Berlin to give the talk, and because we're now remote for now, and a bit of his bio. He is a professor of data science and health at Tilburg University, and the I can't even say it, Geronimus Academy of Data Science. Did I get that right?
You got that right the last time. It's
great.
Painter, fairly well known.
Yeah, for sure.
Yeah, the painter, what his name after.
Oh yeah, that's right. Right. So yeah. I apologize for just mixing it up. And going back to yourself. So Maurits' research work focuses on sequential experimentation and causal inference, and he's also co-founder of the AI company Scalable with an AI, so SCAILABLE. And you can go to scalable.net to learn more about that. So with that, I guess you're going to be teaching us about running AI models in the cloud, and it's a very new innovation that you guys have. So I'm excited to learn more. So please take it away, Maurits.
Thank you. I'm actually gonna turn off my camera because during testing, it seemed like that at least made the kind of imaging from the slides better. So I hope everybody can hear me well and sees the slide. And if not, I'm assuming that somebody from our organization will check in. Yeah, regretfully not in Berlin today. It was fun to be there 1.5 years ago, and I guess regretfully we won't be having dinner afterwards as well. But still, it's great to be able to give this talk and in some ways to be back. Last year, so a bit over a year ago, I primarily talked about my own research work, talked about like multi-armed bandit problems, learning causal inference, and now I'm actually going to talk a bit more about a bunch of work that myself and our team have been doing over the last year on thinking about how to, in the end, how to put machine learning models into production. That's been our main aim. So I'm going to talk a bit about how we end up doing this right now. I'm really looking forward to any feedback. I'm also very aware, just to steal thunder at the beginning of this talk, that I'm actually navigating like a bunch of both data sciencey and engineering kind of topics in this talk. So I'm gonna like lightly gloss over some issues that are much more detailed. So I'm gonna skip over some detail, but I'm happy to fill those in if there's any questions. Let me just go through these slides and see if we can get to the no. Today I'm gonna like have a bunch of stuff to say. Here's a bit of background about myself. Trent, thank you so much for introducing me. So I am indeed a professor of data science and health. Work predominantly at the Euronymous Academy of Data Science, which is a kind of a joint institute between the University of Tilburg and the University of Eindhoven. The latter might be slightly more well-known kind of in the engineering fields. Co-founder of Scalable. I'll be talking a bit about the product, but primarily about what drove us to build it. And kind of as an academic, I'm a frequent author and speaker. So any of these things might be of interest. But let me just dig in immediately with kind of the motivation for Scalable and what we started doing. And actually one of the motivations was a very concrete research project. Concrete research project might not be the best phrase ever, but at least a relatively applied research project where we were working with data that was collected by the Dutch Cancer Registry. And effectively in the Netherlands, there's quite a good system of keeping track of whomever has, well, in a sense, malign cells. So if a malign cell is found in your body, you'll in one way or another enter this registry, and everything that happens to you will be followed and registered, and up until the kind of like the final outcome. And for this specific project, what we tried to do, and I actually talked about some of the methods that we're using for some of this in the last talk, what we tried to do here was learn at the level of individuals what would be the best treatment for specific individual given all of their covariates. And this is a tricky, primarily causal inference problem, and it's a very tricky problem because this data set is obviously observational data. It's not a randomized controlled trial. So there's people that are receiving chemotherapy and people that are not receiving chemotherapy. All of this might be heavily confounded by the kind of background characteristics of these persons. And one of the nice things for this specific type of cancer, so it's colon cancer, was that there is actually a very large-scale randomized controlled trial available as well. So what we were basically doing was trying to, experiment with different methods as confounding in this observational data and checking what we were doing against this randomized controlled trial data. And just kind of fast forward about 3 years of PhD research. So one of my PhD students actually working on this project came to creating relatively simple decision trees, because some of the models we were using initially were fairly complex. None of the oncologists were actually having any of those. So we worked on understandable models and actually got to trees that look like the one here on the right on the slide, basically. So there's a specific stage of your cancer, the specific type of tumor. In this one, it's age as well. That's kind of dictating what treatment we would recommend, or at least like which of these treatments has the highest outcome in terms of life expectancy. Obviously, there's still a whole lot of decision-making attached to then actually making a decision. But we got to a point where actually this model was validated both with a whole set of oncologists here in the Netherlands. We obviously published some of these results. And at some point, we were actually happy to, well, have available, I would say, this model that takes a feature vector, so that's a description of the patient, and gives, we would beg to say, a reasonably well prediction of what happens for both of the counterfactuals, so under chemotherapy and under no chemotherapy. But then it proved super hard, and this is kind of one of the kind of inspirations for the work that I'll predominantly be talking about today. It proved super hard to then make sure that that model was actually being deployed in the hospital. So there's a number of oncologists that would like to use this model, but by the time you want to take a model that in some ways lives on the machine of one of my PhD students and bring that back into the electronic patient records, or at least bring it back into the system that the healthcare professional is interacting with, this is a very long struggle. And I would say it's still a struggle that we're still in. But at least it motivated me to look around and see how people are doing this. How do people move from kind of training these models, especially in healthcare, to bringing them back into the hospital? And what you find is, if you talk to the Dutch Cancer Registry, for example, that this is a known problem. It's kind of very, very hard to bring things, even if they're validated, even if they're accepted by most of the practitioners, to actually bring them back into production. And kind of, if you look over the last decade or so of developments in machine learning or AI kind of in healthcare, but even beyond, you'll find many cases of published papers or kind of case studies that are showing extremely good results and then never really make it into production, into kind of being used on a daily basis. And that's, there was some problem that we hit. So that's much more of an applied problem than a research problem. But we started thinking about that problem. And what I want to do kind of for the remainder of this talk is think a bit about why this problem occurs, and kind of talk about different ways in which people are trying to solve it. Because obviously, it's not an unsolvable problem. People have moved models into production. So there's ways in which people are tackling this. And I'm just going to explore some of these ways and actually present the way that we are pushing now to get some of these oncology models back into the hospital. And I think it's good to kind of, before talking about some of these technical details, just think kind of more abstractly about why this is such a problem. Why would it be hard to move models, even if most of the stakeholders are contributing to developing them, even if these models are validated? Why would it be hard to bring them back into production? And I would say one of the main reasons beyond this is kind of, or one of the main reasons for this, in my mind, is just this kind of, somewhat abstract picture, but it's really clearly illustrated if you think about this Dutch Cancer Registry case, is in effect, there is some real life process. And this is even true for the process that Jim was talking about. There is some real life process in which, in my case, patients are entering the hospital and they're being treated. In Jim's case, it might be consumers that are forwarding money from one place to the other. But there is some process in which data is generated. But then very often, that data is logged and in some way kind of exported from that primary process, basically. And in the Dutch Cancer Registry case, this is in some ways in very extreme, in the following sense, that the cancer registry has all throughout the Netherlands, and the first time I heard this, I kind of couldn't really believe it, but all through the Netherlands, in every hospital, they employ people, and what they do effectively is take data from the electronic patient records, where each hospital will use a different system. There's a few major players in the market, but by and large, hospitals have different systems. And they would copy it to the format that the NCR, that's the Dutch Cancer Registry, actually wants that data. So they really physically kind of almost take that data out from that process. Then a bunch of that data from the different hospitals is being put together. It's cleaned. Models are trained, which some PhD students do their PhD on or graduate on. These models are validated. That validation, by the way, in this specific case, is not even validation back into the primary process. It's validation in the scientific, in the medical literature. And then you have this step where, in some ways, by all of your attempts to make that data as properly accessible, as standardized, as useful as possible, you've really moved away from this primary process. And now you're suddenly stuck with this problem that by the time you hit this validation stage, this step back towards deployment, is hard because you have to move again between different IT systems. You have to move again between different data sources, different data formats, and you have to move between organizations. So there's just a tricky and complex thing to do. And I would say that even kind of on the level of requirements, these processes are very, very different. So in a lot of situations during training, like if we have that model, or if we have the data and we want to build models, we want to just access all of the data available. We want to be able to easily explore this data. We want to fit various models. We want to do like these kind of grid search thing for hyperparameter tuning. We want to, in some ways, work with that data as much as possible and have some kind of ease of use, in a sense. Whereas by the time you want to deploy this model, and especially if you start thinking about deploying like a model like this kind of oncology model back into the healthcare system, well, what you're going to be dealing with just a single row of data. It's just going to be one patient that's coming in. You want to make sure that that model runs in every hospital. And as I said, like, all of these hospitals are going to have different IT infrastructures. It needs to be cheap. It needs to be very well validated in the following sense, that each hospital knows for sure that they're running the right model. They need to know where that data is going if they're sending out data outside of the hospital. So in a sense, a lot of the kind of requirements are very different, I would say, between training and deployment. And a lot of work over the last decades has focused on training and validating models. And yes, there are ways of now deploying models, but I think that's still a very large problem. And kind of in this space, I think there's a bunch of interesting things to do. So let me just skip ahead and talk about some of the ways in which I guess people are now deploying things, because obviously, like, people are bridging this gap in one way or another already. And I think one of the core ways. And again, here I'm kind of making some kind of a few relatively broad statements, and there's multiple systems that would allow you to move from model training to model deployment. What I'm going to talk about is different, in some ways, different flavors of doing this, although there's all kinds of different specific cases of it. But I would say there's a few distinct flavors of moving from training to deployment. And one is kind of this simple idea, is what I would call just containerize as is. It's train your model, use whatever you want to use for training your model. Use TensorFlow, use PyTorch, or use your R package, which is still definitely a lot used in the healthcare sector as well. Use this to train your model, and by the time you want to run inferences, by the time you want to create predictions, you take all of that code, you take that fitted model, and all of the software that was one day written to actually predominantly for training these models, wrap them into some container, like a Docker container, is what a lot of people are using, expose a REST API, send your data there, send it back, and that's kind of the way in which you would deploy. And that's actually quite a good solution in many cases, for various reasons. One is it's actually fairly easy to carry out. So you can take whatever you had and whatever you built, and just wrap this container around it, and you can spin it up and start creating inferences. But there's also a bunch of things that make it somewhat hard. I would say one of the predominant things that has been bugging me about this approach, which might not bug everyone, is that to me these approaches feel super bloated. Like Docker containers, they run a lot of stuff. And if you really start thinking about what some of these models do, they run an amazing lot of stuff that you don't really need to do the simple kind of matrix operations that are often involved in just generating these inferences. So you have this very bloated thing that is running these inferences, and it's kind of usable, but it's slow, or at least kind of comparatively slow. And one of the other things that kind of is additional to this in the healthcare world is that often what people do when they're setting up these Docker containers is eventually deploying their models on some kind of cloud and opening up some REST API. And this is something that a lot of people have tried with the NCR data and with models that are being built on top of that. It's just put down a central server and let all the hospitals integrate with that central place that's actually serving these inferences. This is something that most hospital IT people don't like. They don't want to integrate with external servers. They don't know what's running there. They also don't want to necessarily send patient data to some external server. So even if you set it up this way, you would have to move it in-house, and you would have to deploy all of this kind of at the level of the hospital. But still, it's one way in which people are deploying models. Another way I think that people are deploying models, and I see this more and more also kind of in my work with some online marketing companies, is that people actually want a lot of performance. And if they want a lot of performance, what they do is they fit some model, and by the time they have a model, they have all the parameters involved in the model to generate the inferences, they'll effectively just rebuild it into some kind of, using some lower level language, rebuild it, compile it, and have, in the end, just an executable that is specialized to just create these inferences. Now that's very fast, and if you do it well, you can actually like compile to different targets maybe and move it around and run in the different hospitals. On the other hand, I would say it's extremely time consuming to do, because now you're rebuilding these models. And many solutions that are offered take one of these two approaches, or like try to automate some bits to move parts to a lower level language. But I would say by and large, it's not necessarily a solved problem yet. One other solution that I actually saw, which I thought was interesting, and it's being used by one of the bigger e-commerce companies in the Netherlands, they were actually using their model deployment in the following way, where they're just saying, okay, what we're going to do is we'll train these models, and since we're unable, which is effectively what's happening for them, to generate inferences fast enough, we're just going to take the distribution of all the input vectors, take canonical cases for all of the input vectors that we're expecting, run predictions offline, put them in a database, and by the time somebody visits our website and we need to generate an inference in kind of the microsecond that the page loads, we're just going to pull it down from our database. So there's still these several ways in which I would say people are doing this, with various advantages and disadvantages. So I would say kind of the Docker container style deployment is simple in many ways, or at least conceptually simple, and very shorthand, I would say it's bloated. Rebuilding stuff in lower level languages is hard, but could potentially get you very efficient inferences. And then there's these kind of offline, online models that might be appealing as well for various reasons. But really, we started talking about that in this project, and kind of thinking about how we could take that healthcare model and take that to some of the hospitals. And we wanted to make sure, I just scrolled through a bunch of slides. We wanted to make sure that these models are performant by the time that they get to the hospital, that they're running, that they're small, and that we just have efficient inferences, which in some ways for the oncology model might not be the first kind of requirement that comes to mind, because here often the input features are quite small. But if you're thinking about imaging types of data, you definitely want some kind of performance. So I have a few slides, I guess, on an intermezzo of why am I even saying that rebuilding stuff in lower level languages might make model kind of predictions or might make inferences more performant. Let's dig into a few of those slides. So I would say if you start thinking about, oh, if I have a trained model, so I'm really talking about we've already built this model, everybody thinks it's a useful model to think about whether people should get chemotherapy or not. We've all validated it. How do we make sure we generate fast inferences? Well, I'd say one thing is just making sure that we have, strongly typing, typecasting, compilation, like all of these things moving in some ways between even programming languages that are easy to use to programming languages that are much more performant. So there's a whole bunch of things that you can do if you know exactly what is supposed to happen to make sure that code runs a bunch faster. And it's not just the typecasting. I would say it's memory management that is giving you a whole lot of performance. But finally, and I'm just skipping over some of these slides, but finally, what I really think is kind of hindering performance in a lot of inference tasks currently is all of the layers that are being put in between. So if you think about this,
We can't hear you anymore. You are not audible. Hello.
Well, probably on my end, the Netherlands, it's tricky. Once you get to Germany, it should work. But, so what I was trying to explain, and I'll just pick back up here, is kind of how we're trying to make that process of deployment easier. And effectively what we're trying to do is allow people to just use kind of whatever tools they're using for fitting models, use this kind of simple layer in between, the scalable Pi package is what we start to call it, to transpile models to WebAssembly. I'll talk a bit more about WebAssembly in a second. And the reason for doing this effectively, and I'll just skip to some of these slides, is by using WebAssembly, in effect, we can generate inferences at pretty much native C speed. We can remove a lot of these layers in between because we can have extremely efficient runtimes just for running these WebAssembly packages. And what I think is appealing in kind of this health context, and I'm not sure if that comment was left out when you guys didn't hear me, but one of the things that I think is extremely appealing is that we can now have these kind of, in a sense, executables that will generate inferences, and that can run on various systems, and you can effectively send to the hospital. So instead of sending data out from the hospital, we now have an efficient model format that we're able to distribute over all these different hospitals that want to run their inferences on their own systems, and all we do is send them the model the moment they want to use it. Just as a kind of comparison as to, I hope that I'm not just talking bullshit here. Actually, like doing this conversion to WebAssembly of some of these models gives quite a big increase or decrease in the size of the model specification, which means you can more easily send it around, run it more easily, and also just kind of gives you quite a bit faster evaluation time. I hope you guys can now all hear me, because now I've noticed I've had the tendency to slow down, but that doesn't necessarily help, obviously, in kind of you guys hearing me. So I wish I could confirm that things are working. Awesome, that's good to hear. So I have a few more slides. I don't want to take it too long. Maybe there's questions as well. I have a few slides, kind of an intermezzo on WebAssembly, and then I'm just going to wrap up. So we're using WebAssembly. Talk about what is WebAssembly, why do we choose to use WebAssembly. So WebAssembly is this binary instruction format. I would think about it, it's just a compile target. And by now, despite the name, which I guess is in many ways poorly chosen, it is just this kind of target to compile to, and you have this executable is one way of thinking about it, that you can run in all kinds of different places, that runs in an extremely small runtime, that by virtue of kind of a history of being developed for the web, is also inherently secure. So the I/O is actually quite tricky, but once you have that done, you have this small package that you can move around, that you can run very fast, and you can kind of guarantee that whatever model you're sending to people is actually what they're getting. And right now, like, there's a big ecosystem for using WebAssembly. One of the cool things that we have been able to do through this kind of philosophy, so moving models automatically to WebAssembly, is also deploying them on kind of on the edge or on various IoT devices. So we think that our kind of idea of model deployment through WebAssembly just combines both ease of use as well as speed, and opens up on a whole lot of different places where you could actually run this model. I guess right now it should be relatively easy to compile to WebAssembly if you're building your own. Obviously, like, we are providing this package to move to WebAssembly. We currently just provide a service to run WebAssembly packages that have a specific kind of I/O and that have a few specific exported functions. Those are the ones that we're now shipping around, and those are the ones that we're running on various devices. But all of this is kind of, I would say, fairly well documented, and I hope we're able to share the slides with all of these links in there, and you should be able to find all of this. So just to kind of do a very short demonstration, and then I'm happy to take some questions. So here's just a very small bit of code, and I'm just gonna kind of zoom into this a bit. Let's see if I can. There we go. So how this process actually works, and kind of the example is in some ways too trivial to even show. But what we're using here is just a very simple scikit-learn example, just generating some data, training a model the way you would normally train a model. And really the only thing we do is just upload, using the scalable pipe package, this model, the fitted model, to our servers. We'll compile it to WebAssembly. You can download it as WebAssembly or immediately just consume it as a REST endpoint. That's the way we're now trying to make it extremely easy to kind of deploy these types of models. We have a very cool video. It's not the best, and I'm not even going to try to show it due to some of the technical glitches right now. But once these slides are up and you guys can click around, you're definitely, like, feel free to look around afterwards. I think I've talked about most of, like, my motivation or our motivation for building this. So in some ways, we ran into the problem of model deployment in healthcare. There's a few things that maybe are specific for healthcare. It's like, oh, people don't want to move all of their data around. But on the other hand, I think there's a few things that are also just relatively general, that often model training is just a very different process from model deployment. And what we're trying to do is bridge that gap, and we're definitely not the only ones trying to do so. We just think that kind of WebAssembly as an intermediate format for model deployment is an extremely useful tool. And in any case, like, if you haven't played around with WebAssembly yet, I would strongly encourage you to do so, because it's also just fun to do. I'll share a bit of where we're trying to go right now, and then I'll wrap up. Really, currently, we effectively can take any scikit-learn model, move it to WebAssembly. We can do stats models, XGBoost, and we're almost there supporting ONNX. We're now supporting ONNX 1.6, and 1.7 is, I guess, the newer version. And with ONNX or Onyx, whatever way you want to pronounce it, I guess we have a very kind of large set of models and even pipelines that we can convert to WebAssembly off the bat, kind of automatically. All of this is just available as a web service, basically. Then we currently have a number of runtimes as well. So we did, great. Oh, I zoomed in too much. There we go. We currently have a number of runtimes. So obviously, like, all of these WebAssembly packages will run on the browser because that's what it was initially used for. We can run them on our servers and host them as a REST endpoint, but we currently can also just host them on various kind of edge devices. Some of these runtimes are available. Some of these runtimes are also just easily or very easy to create using some of the tools that the people from Wasmer have created. And there's some links to that in the slide deck as well. So we're definitely moving towards also deploying some of these models on kind of on the edge or on various different cases. And finally, which I think is kind of cool, we're trying to even strip more layers and do kind of these unikernel deployments, where in effect, like, all this machine is doing is running this one inference task that you're trying to do. I'm gonna wrap up there. Actually, like all of this is available. If you go to like scalable.net, you can try all of this, and we're just like hosting it right now. And right now it's for free. We're in beta. We actually don't know yet like where this is going. We might be opening up all of it. We're currently predominantly trying to get some of the hospitals to use it, but in parallel, we're really looking for feedback from people that are just playing around with this, that are using this deployment through WebAssembly, and we're trying to see where it's useful, and maybe it's not, and then we'd be happy to know as well. But right now, this is kind of where we're going. So I'm gonna wrap up here. I'm again sorry for kind of losing you at some point. So I hope I picked back up and kind of everybody was still in. Looking forward to answering some of the questions if they're there. Thank you so much. I'm gonna.
Thank you, Maurits, very much. Thank you very much for your talk. Yeah, you definitely have a point there, no question about it. There aren't actually too many questions. There was one question that you actually answered in your last slide. I have a follow-up question to that one, since it now takes, so you're integrating Onyx into your WebAssembly. Yeah. Does it mean that it now accepts any deep learning model?
Yeah, pretty much. Like there's still a few challenges of doing all of the I/O for the different formats, basically. Like what are like how do you make it in some ways user friendly to send a feature vector to this WebAssembly binary. But in essence, like all of like PyTorch TensorFlow will easily export to Onyx, and we can pick up from there and transpile to WebAssembly, basically.
Cool. And just to make sure that I understand you correctly, this then runs on CPU, not GPU.
Yes, although I would say it should be so people are working on kind of GPU support for WebAssembly executables, basically. But really what we are considering, and here is, but maybe you have very different use cases in mind. But for me, like most of the GPU use cases are on the training side, basically. It's when you have shitloads of data that you're iterating through to train your models. Whereas on the inference side, I think very often, actually the number of computations that need to be done are at least relatively limited if you compare it to training. So what we find is that a lot of these models in healthcare, for example, they'll take one image as an input or one feature vector that's not even that big, it's just a description of the patient. And doing all of that, like doing those operations, there's no need for GPU, basically, on the inference side. And one of the things that I maybe didn't really talked a lot about is even like if you think about a model that you store. So if you store like a scikit-learn model, for example, and whatever way you necessarily want to do it, but often what you store is the model parameter. You store a bunch of summaries of like model performance. You might even, depending on what you're actually using, store bits of the data or even all of the data. And all of that, if you just move kind of mindlessly to deploying your model in Docker, you would move all of that, basically. What we really try to do, and we're even doing this with all of the on the next one, is just strip everything you don't need to generate all of the inferences. So if you think about the simple linear regression example, actually the only thing that's in that WebAssembly package is just the few parameters and the linear combination that you need to do the inference. All of the other stuff is stripped. So you have a very small package to generate these inferences. We're trying to do the same things with Onyx. This is why it's a bit challenging, because we kind of have to dissect pretty much all of it, and it's a fast-moving ecosystem, and we're in some ways trying to keep up. But that's, one of our main ideas has been like, let's just effectively retain only the things we need for inference and wrap those as efficiently as possible into this WebAssembly binary.
Back to the data set you are considering, this Dutch cancer data set. In what way is it used right now? So you say lots of people in academia are working with the data set, are building nice machine learning models on it.
Yeah.
But you have difficulty deploying it. But in what way is it used? Is it used at all, or is it just
Yeah, it's definitely used. So it's used for various reasons. The whole effort, the whole data collection effort, was conceived as registry data and kind of purely for descriptive statistics. Like one way of thinking about it, purely for descriptives of what's happening in the Netherlands, in kind of in this space, basically. And that's what it's used for all the time. Over the last few years, people have been trying to use it more and more to kind of learn causal effects, to maybe kind of learn individualized treatment rules. It's what we were trying in this project. But what you see is that those would only make it back to practice by effectively being published in some of the scientific literature, then being discussed. So all the oncologists, they have their own kind of groups where they discuss the guidelines, and then maybe a model like this might have an impact on the guideline. That is just kind of the set of rules that people are using to make these treatment decisions. And it has been, like, it has proven super hard to actually get a model kind of to be just used in real time. So I think the kind of standard way in which this works is just, some of the results from these models, they might translate into practice by just being included into the guidelines, by being discussed, but not necessarily the model one-on-one being used in the hospital. And here is one thing that I find in some ways somewhat tricky, and this is a maybe a later concern, is if you are using these models and they make it to the guideline, and this is even a question maybe to Jim about his first talk if we have some time, but by the time you have a deterministic guideline, and you're using that all the time, then your data is not going to be super informative anymore for learning new things. So I think there's also this really big kind of discussion about like how much of this should go into the guidelines, how much of this should we be exploring, how much freedom in a way should oncologists have, and kind of these models being input as just one of the various kind of things that are driving the decision. But to just shorthand your question, right now, hardly any of these models are making it back to practice. They're making it into publications.
And did you, I mean, it's, I guess, also hard to work with in a medical sector, in a sense that they are maybe not very tech savvy. Is it easy for, I mean, have you build a prototype and showed it some doctors how to use it, and did they actually like the interface and what they can do with it?
So we have two parallel things there. One is we just have like this R Shiny app that some of the oncologists were able to play with, which is obviously not the way we actually want to deploy it, but that's how some of the doctors got to interact in a sense with the model. And one of the things that is kind of also part of this modeling effort is that you have to consider like the cost of the treatment, and those are not very clear. Like, if you're only considering the monetary cost, it might be clear, but if you're considering like some of the adverse health effects of these chemotherapies, so there is in a way like we've done some of these models where they could interactively like play around with the cost and then see what the results of this model would be. So that was in our communication to the oncologists. And I would say, by and large, my experience has been, but obviously those are only the oncologists that talk to us, but my experience has been that most of them are convinced that they are collecting this data, that should be useful. And they believe, like, they're definitely willing to put in effort to kind of think along, and even to sometimes say, hey, that's a super weird result that you're getting from this model that can't be right. Like, there must be something wrongly encoded, and that they like even contributing a bunch of their knowledge. So my experience with some of the oncologists is that they're willing to do it as long as we're making this relatively visual for them. On the other hand, we're actually now starting with one Dutch hospital a pilot where we're actually implementing not this model. It's actually another model that has already made it into the guidelines, where we're implementing another model using WebAssembly into their ecosystem. But there we're yes, there is an oncologist that's supporting the project. Like, she is saying that she would like to have this like on her screen or like accessible. But in the end, we're just interacting with the IT people from the hospital that are actually like maintaining infrastructure. So there, you're moving between these different kind of groups, basically. I still think like for any of this to work, it definitely helps. And if not, it's a necessity to have some of the kind of the people that are actually like delivering the care to be interested and to be involved.
Yeah. Thank you very much. Awesome project you're working on. Good luck, and I hope you make lots and lots of advances
Thanks
to
so
the
much.
advantage of lots of patients. Yeah, awesome. Also, Jim, thanks again for your talk. And I think that wraps up today's talk. So I give back the mic to Trent.
Yeah, well, from my side, thanks very much as well, Maurits, for the great talk, and also once again, Jim. Really, useful tools from both sides and great learning. So that's it from myself. For the whole audience out there, remember we are always the first Monday of every month. We've already lined up the speakers for next month, so we continue to do that. And you can check our meetup.com website to learn more, of course, as usual. And maybe I will hand off finally to Abhishek for the final note in closing.
Thank you everyone for joining, and I hope you enjoyed the meetup. There were some technical issues, but not for long, and I don't know why it happened. I didn't even touch anything. So I apologize for that, and I hope to see you guys next time. Bye.